All right, here's some more circle examples. I'm doing this for a reason, because we have this scenario here where we have compression here and tension here. I have another one where I have compression and compression, and another example where I have tension and tension. And I'm doing this for a reason that will become clear in a class coming up pretty soon. So anyway, we have this instance. So the first thing we want to do is plot out this face right here. So we plot out this face, and we have a negative 62, and we see that this is clockwise, so that actually comes up to the upper half right here. So negative 62 looks like it could be, all right, so these are at 60 and 80, so it's actually really close, tight in there, right? So very, very tight inside there, in between the lines. Because so every denomination here is 4 apparently. So this should be 42. So there you go, 40 right there, and so it is also close in there. So I'm going to say that's going to be my point. Did I get that? It looks pretty good. Once again, my lead is really fat. Now I want to plot this point right here. I have negative 94 and still have that 42, but now it's going to be counterclockwise. So it's going to be in the lower half down here. So we have 94, which I'm going to, okay, so this is 80, so it's 84, 88, 92, so kind of like right in there. And then this is the 42, so looks to be like right in there for me, right? So it's tight, but nice to use a bigger graph paper or a thinner pencil lead. I do have a thinner pencil. Let's see, that's a 0.5. Well, it's gotta be better than what I'm using right now. Okay. All right, so I can't quite see that very well, but I think I got it. All right, so you can see that right there is where C is going to be. Right there, right? If I'm writing out what C is, just going to be the average of those two, right? So it's negative 62 plus negative 94 divided by 2. I end up getting a negative 78.00. These are in megapascals. Right there. So that's, yeah, 78, sure, right there. You see it's near negative 80, so it's just the side. Okay, now I want to get my radius onto this thing. Sometimes I go ahead and draw my circle now. You know, it really depends on how sharp you make that right there. It's a really important thing, and I don't have like, usually you have like this little sandpaper stuff, and I don't have it, so I'm just going to do the best I can. That's not terrible. It's not terrible there. Okay. Now I'm going to say that this is my radius right there. I tried to make a little bracket looking thing. So the leg of that radius is going to be 78 minus 62, right? Because that right there represents 62 right there. So that's going to be the leg of that radius. So I'll say 78, and I'll leave off the zeros, minus 62 squared. Plus, and then the vertical leg is just the 42. 42 squared, and I should get 44.94 megapascals. All right? Now, the principal stresses are going to be this guy right here and this guy right there. That's going to be sigma A. I'm going to call the larger of the two sigma A, and the smaller of the two sigma B. Right there. So sigma A is C plus R, right? Or negative 78 plus 44.94. So that ends up being negative 33.06 megapascals. So sigma A is 33.06 MPa compression. Box it. sigma B is C minus R, or negative 78.00 minus 44.94. So it's going to be a more minus thing of negative 122.9 megapascals. So sigma B is going to be 122.9 MPa and compression. Okay? And if we wanted to find tau max, that's just going to be equal to R right here. So that's that right there for the time being. It's going to change in the next class. But that's an example, another Mohr circle example. Here is yet another Mohr circle example. And here's one where we have tension on each side. And so we do the same procedure. We plot the face. We have 31 and positive 31 in tension. So there's going to be, let's see, these are counting by twos. So it's somewhere like right in there. And this is clockwise of 17. So it's somewhere here. So there's 2, 4, 6, somewhere in there. So let's see. Coming up here, 2, 4. Yeah, somewhere in there. Oh, and by the way, I should have checked graphically with my answers right here. That's one of the reasons why we're doing it graphically. So I should point this out right here, that we could see that we got, yeah, 33.0. We can, if this was larger, it would really help us. We can see the 123. Yeah, that's like, it's greater than negative 120. So you can kind of see that this Mohr circle is kind of telling us, confirming for us that we're doing the right thing, right? It helps us in that way. It's going to really help us when we go to do 3D Mohr circle, which will be a new thing for you. All right, and I forgot to plot out the points. I didn't label them. I usually do. So let me do that right here. It's good practice as a sanity check. So we have 31 and 17 is that point right there. We'll plot this is going to be, actually I did a bad job of plotting it. That's one of the reasons why I waited until I was done plotting both points to actually plot the thing, but we'll see that in a second. Go 67, so that's like 68, so just a little bit shy of that. And then I'm plotting that point right there. This is counterclockwise, so it's down below, and it is 17, so it's somewhere right in here. So I'm going to say like right in there. So we plot that guy in here. So right there is going to be my C, and I'm going to choose this side for my R. I'm going to draw my circle now. And it's looking pretty lopsided here, so I probably made a pencil lead mistake or a plotting mistake. Yes, I did. That's always aggravating, right? I don't know what I did. That looks like 31. That looks like 17. That looks like 67. Yeah. Oh, I think I didn't. If anything, I think it needs to be a little bit like that's 18. So it needs to be a little bit further down, like right there. That's what I did wrong. And it wouldn't hurt to use the other. Oops, that's why I use a thick lead. I can't stand that. I put too much pressure on this thing and I break it all the time. There you go. That's a little bit better. All right, so let's see. Let me see if I can get a little bit better of a job of it. I mean, this is the whole point of doing it graphically, is to as a double check. That you're making sense of the thing. And to go back, and if you get something that doesn't make sense, to go pick it apart. So labeling these points right here, this is the 67 and the negative 17. And this right here is the 31 and 17. All right, so now I've labeled them. Here is C. Here's R right there. So C is going to be my 31 plus 67. It's the average of the two. That comes out to 49.0, and these are megapascals. And you can see it's just to the side of 50, so I did a better job once I corrected it. And my radius here, I'm going to say this leg right here, that leg is C minus 31, right? So it's going to be the 49 minus my 31 squared. And then this leg is, as always, going to be the shear. So for my radius, I get 24.76 megapascals. Right? And so if I have this is going to be where my sigma A is. And here's going to be my sigma B. Right there. And right above where the center is going to be my tau max. I didn't label those on the other ones, did I? I should have, like right above. Tau max. For the time being, we're going to change that in the next class when we do the 3D Mohr circle. So sigma A is just going to be C plus R, which is 49.0 plus our 24.76. So that ends up being 73.76 megapascals, and that's in tension, so I'm going to write that right there, and I can actually box that up. And then I have a sigma B is going to be C minus R, right there. So that's 49.0 minus 24.76. So sigma B is 24.27 megapascals tension. And then this, as has been so far, the absolute maximum. Oh no, excuse me. I said there. Don't say that. Not yet. It's not the absolute maximum. It's just the maximum shear is going to be equal to the radius, which makes sense, right? Because this is the maximum shear that's going to be possible. And you could rotate this any way that you want, right? You don't have to do this. This is showing, the maximum right here is showing that we're rotating the thing this way so we can get those aligned right there. But you could rotate it anywhere you want, and that's going to give you a different combination of shear and normal stress, depending on what the orientation that you decide to choose of, like a little box that you draw on the piece. That's all this is right here. But it does have actually even more of a physical meaning, or maybe I don't want to say the physical meaning. It does have physical meaning, but also has sort of like a more universal meaning. So let me actually pause this and show you MATLAB really quickly to get the eigenvalue version of the thing, right? So in the notes that I have right here, let's see, whoops, boom. We went through there. Here's like examples, example. All right, so I talk about the eigenvalues. What you could do is you could set this up as a matrix. Here it is in 3 dimensions. You could set this up as a matrix and find the eigenvalues for the thing. And what that really is turning it from this populated matrix into a diagonal matrix, and that'll tell you and these become the principal things. So what you've really done is you've cleared this way by getting rid of all the things in the off diagonals in essence when you do that. And here is the MATLAB code to be able to do that, right? So and I'm not going to do it by hand. I think I have in other semesters. I tried to, but I don't think anybody learned much from that experience. I think I might have a video where I did it in there, but it was ambitious. That's what that was. It was ambitious. So let me pause this, and I'm gonna log on to my computer at work and get MATLAB running. Okay, so here it is. Actually, I forgot that there's MATLAB online, so I can actually use the online version here. And so I have, here's my notes that you can just go ahead and open up the PDF and go Control C, highlight those things, and I believe they'll just paste right into, this is a new M file, right? And so new script file. So instead of like saving it as anything, I'm just going to highlight this. Okay, so recognize this as being that first example, right? Negative 13.1 and 18.4 and 27.9, right? So if I just go ahead and hit evaluate the selected right there, it solves it. And you can see down over in here, here's the solution. So you go to, we could go to SIG, like you could just write out what, let's see, we'll write in D. What is just D? D is, these should be the principal stresses if you just type in D. Negative 29.38 and 34.68. Right, so if we go back to what we just calculated a second ago, right. So right there we had 34.69, right, and negative 29.39. 29.39 right there, right? So those are the principal stresses. It's an easy problem because there's just two dimensions. If you the other thing that we can find from there is this V. Those are the eigenvectors, and there's it takes a little bit more work to explain that. What these are is these are the vectors orientation of the new axis that you would need. So these are unit vectors. So if you were to plot these out, you would know that these would be perpendicular to each other, and they would represent what the new orientation would have to be of the axes. So you could actually use this and figure out what the angles that you would have to be for a rotation. But you could use this to try to solve these other problems. Like, for instance, we had 94, let's see, they're both compression, so they're both negative, 94 and 62, and then we had 42, and honestly, it doesn't matter what direction that goes, right? It just, because it's going to flip-flop which direction that you have here. So plugging into here, we take a negative 94. No, I guess no. I'll do it correctly. Negative 62. Sigma y. Now that's going to be a negative 94. And tau, right there, xy is going to be equal to 42. And everything else is just script. We evaluate, and so then let's see what D is. D is a negative 122.9 and a negative 33. And what do we have? 122.9, right, compression, and a 33 points there. So you can see, I think you believe me, right? Or we could do the last one too, just in case you don't believe me. That we can, let's see, for that problem we had positive 31, positive 67, and a positive 17. It won't focus. There you go, 17, right? So 31, 67, and 17. So that's positive 31. This is a positive 67. And this is a just 17. And it doesn't really matter whether it's positive or negative. And so let's see what we have for D. We get 24.2 and 73.75. There you go. We got the principal stresses by getting the eigenvalues. We could also, we could also plug and chug, but this is, it's confirmation. Hey, maybe use a MATLAB for something, right? And I ask you, what do the eigenvectors represent? They really represent, like, you'll see that, like, on here, we're really plotting 2 points, right? So they each represent a point and a point, and that's like the orientation of the now what the x and the y have to be in order to achieve this result right in there. Now, have you used eigenvalues and eigenvectors for other things? Because you will. It's a pretty important tools. And it makes life a lot easier for three-dimensional stuff, right? So three-dimensional stuff, where we have x, y, and z normal, and we also have the other potential stress, shear stresses. You remember from it might be from the first class, I drew out these. Did I? No, I think it was class 2 where I drew these out, right, to give you sort of an idea of, like, okay, here's all the different stresses that could possibly exist. Well, now if you want to get the eigenvalues and the eigenvectors, it's a lot more work. You don't really want to, the Mohr circle is kind of tough to do. We could still do 3D Mohr circle when it's plane stress, but when it's more complicated like this, we really need to use the eigenvectors. So I wanted you to have experienced that. So that's it for this video, and hopefully you gain some appreciation of doing Mohr circle. I think maybe I should have, by the way, talked a little bit more about what this is. You notice this is just a simple command, the EIG command, and you could just do a search on that. You could do help on EIG right there, and it'll come up with a help window eventually. I think it will. Actually, I don't know how that works in the online version. It might be taking some time and confused. Oh, maybe it's this guy right here. I don't know. I don't see it. Anyway, in regular MATLAB, you'll be able to do that. I think it's like all stressed out because I did that. I don't know. But anyway, I didn't eat dinner, and it's like 9 o'clock at night, so I'm gonna go eat dinner and be done with this video.